Okay, well, I'll get started. Um, since we got a couple introduction slides here. And so thank you for calling in to today's webinar on the gentle introduction to optimal design. This is one of our quarterly webinars that's hosted by the Statistics and Pharmacometrics Interest Group. So Tim, can you go to the next slide? So I guess I should say as well that the seminars, the webinar will be Dr. Tim Waterhouse will be our presenter, and then Dr. Julie Bertrand will be moderating the Q&A discussion. And so we're all involved with the Statistics and Pharmacometrics Interest Group. This is a joint interest group chartered by both the International Society of Pharmacometrics and the American Statistical Association. It's free to join. We have the QR code on this slide and then on subsequent slides. So please reach out, or if you want to go to our website. Tim, if you go to the next page. So our website here, if you go to it, it gives some information about us. We were formed in 2016. The idea is that we would be a group that could help bridge the disciplines of statistics and pharmacometrics. If you go to our webpage, we have a lot of information on statistics for pharmacometricians, pharmacometrics for statisticians, lots of information that can be used for training or for learning more about either statistics or pharmacometrics. It's just a really good resource, and it's being updated pretty frequently. So we're trying to be actively managing this. And I think it's been, for the feedback we've gotten, is this website's really nice. So next slide. So we do have some updates. We did send out an email asking everyone to vote for the new steering committee members. We do have to have half ASA representatives and half ISOP representatives. You don't need to be a member of either. But there was an email sent out last week. Please check your junk email if you haven't seen it. And we do want to have all the voting completed by April 7th. Just a couple other updates. There are some deadlines coming up if you want to attend the ASA biopharmaceutical section, the regulatory industry workshop. So they have the roundtable deadline in 2 days, and then the poster deadline's April 11th for submission. And then the American Conference on Pharmacometrics, their abstract submission deadline is May 15th, but the outcomes are open at the moment. So please join our special interest group. And I think it is a good resource, and we're trying to be more actively involved, and it's free to join. So, and then please look out for that voting email that you should have received last week. So next slide. So our presenter today is Dr. Tim Waterhouse. He works at Metrum Research Group. He's been working there since 2019 in both PKPD and statistics. He earned his PhD in statistics from the University of Queensland, where he applied optimal design methods to PKPD models, and then he worked at Eli Lilly and Company in pharmacometrics before joining Metrum. His work involves using modeling and simulation to inform decision-making in all phases of drug development across a range of therapeutic areas. With that, I will pass it over to Tim. And we can get started.
All right, thank you, Luke. All right, so thanks for the introduction, Luke. So I want to talk to you today about optimal design. And this is a topic that a tool that I think is underutilized in pharmacometrics. And I think it's fitting that this is presented as a stats and pharmacometrics webinar, for me at least, because this was my gateway drug from statistics to pharmacometrics. As Luke just mentioned, this is my PhD topic, which brought me into the world of PKPD models. So I'm going to talk about the concepts of optimal design and some of the tools that we have available to do this. In particular, some free and open source tools. PopED and PFIM are a couple of R packages, and then I'm doing the simulation involved in some of these designs with mrgsolve. So I'd like to acknowledge just at the top some of the collaborators that have helped me put these slides together. Kyle Barron, one of my colleagues at Metrum, helped put together some of the mrgsolve models. And Julie Bertrand and Romain Leroux at Interim in Paris helped me port some of the examples from PopED to PFIM. So I gave a version of this webinar a few years ago using PopED, but since then there's been a release of PFIM as an R package. So we wanted to include that here too. So why are we talking about optimal design? Why do you need to know this? So suppose you want to design a study, and that, assuming you're some kind of pharmacometrician, you want to fit some kind of model to the results of that study, and you don't want that model to fail spectacularly. If your model is not designed, if your design is not, if your study is not designed well, then you won't get a good model out of it. So you can assess the study design using simulations. So you can repeat this study design many times, refit the model to it and see how it performs, but this can be time consuming. So I'm going to show you how to do this a little easier with optimal design. So I'll talk about some background on optimal design, introduce some of the tools that we have available, including, as I mentioned, PopED and PFIM, and start with an example of a simple model. And I'm going to go through this with both PopED and PFIM, showing you how you can evaluate a couple of designs and optimize the design if you need to, and then run some simulations to confirm those results. There are some more complex models that I'll go over, and I'm going to use PopED and mrgsolve together to do these. So these involve solving differential equations, which mrgsolve can help with. So let's start with some of the concepts. Optimal design, at least most of it, is centered around this object called the Fisher information matrix. So on the right here, we have a nice looking Fisher, and on the left, we have the equation defining that matrix, which has nothing to do with the animal. I just thought it looked nice. Without going into the details of what's on the right-hand side here, I just wanted to point out that the matrix itself is a function of our parameters, this character here, and this would be our thetas, omegas, and sigmas in non-mem language. And then we have our design variables. So this is your PK sampling times, or your doses, or the number of subjects, and so on. So you need both of these objects to construct your information matrix. Depending on the form of the model, the form of this likelihood, the right-hand side here can get very complicated, but I'm not going to go into exactly how we generate these. I'm going to show you how the tools that we have can calculate these for you. So why do you care about the Fisher information matrix? It's because of this result called the Cramer-Rao lower bound, which says that if we take the inverse of that matrix, we can get a lower bound on the covariance matrix of our parameter estimates. And this is important because it gives us a lower bound for the standard errors that we can expect just by taking the diagonals of that inverse matrix. So we have a very quick way of evaluating the precision of our parameter estimates. So instead of repeating a large number of simulations and then refitting our model to those, we can do this in one quick step by just calculating this single matrix. All right, so why do you really care about it? Well, there's a large number of optimality criterion in optimal design, which involve the information matrix. The most common one, and the one that I'll talk about today, is the D optimality criterion. So the D here stands for determinant. So a D optimal design will maximize the determinant of that information matrix. And we do that because maximizing that determinant is equivalent to minimizing the volume of the confidence ellipsoid of your parameter estimates. But what does that mean? Okay, so the confidence ellipsoid is just a fancy word of extrapolating confidence interval to multiple dimensions. So for one single parameter, that means just shrinking down your confidence interval as much as you can. If we extrapolate this to 2 dimensions, say we have parameters for clearance and volume, we want to make this confidence ellipse as small as possible. Okay, so recall that this information matrix depends on your parameters and the design. If you have a linear model, the derivatives involved in calculating that means that those parameters would drop out. By linear here, I don't mean linear in the PK model sense, where you have a dose-dependent linearity in your PK or linear clearance. This is a straight statistical linear model. But for nonlinear models, including what we would call a linear PK model, this is no longer the case. So our information matrix depends on the parameters that we're trying to estimate. So if you want to design your experiment to figure out what those parameters are, then you first need to know the values of those parameters. So this is kind of a catch-22, but it gets worse for nonlinear mixed effects models because the likelihood involved in calculating that matrix has no analytic solution. So just like when we fit nonlinear mixed effects models with MLE methods, we've got to find approximations to that likelihood. So we do similar things in calculating the information matrix. So our Fisher information matrix is an approximation to a lower bound that depends on the parameter values. But all is not lost. For the last point here, yes, it depends on the parameter values, but we usually have some good information on what those parameter estimates may be. You know, drug development is a learning process, so we've usually fit some kind of model to this data, similar data before. Maybe we're moving into a new population for this study, so we have some uncertainty about what those parameters may be, but there are ways of dealing with that. And we have to deal with this dependence on parameter estimates, whether we're doing a simulation approach or an optimal design approach. And for the approximation to the lower bound, this is something to be aware of, but it's usually something that's not a huge issue. I would suggest we always run simulations to confirm these results because of this approximate lower bound, but the results that we get from simulation are usually not far off from what we get in an optimal design output. I'll talk a little more about simulation. So the topic I'm talking about is called optimal design, but the designs that we actually use in practice are rarely optimal. So there's two ways that we can use what I call optimal design. So we can actually optimize a study, or we can just quickly evaluate a study or a handful of studies. So as we've seen, we can use that single matrix calculation to calculate RSEs, relative standard errors. Optimization itself is often a last resort. So you can evaluate a few candidate designs. So you might have some kind of intuition about what kind of PK sampling or what kind of doses you'll need in your study. And so there's no need to resort to optimization. But if you're in a situation where you have tight constraints on resources, say you can only take a small number of PK samples, and the model or the design is complicated enough that our intuition no longer works for us, then we have to go to optimization with some kind of search algorithm. Okay, let me talk for a minute about sampling windows. So I just said that the optimal designs that we use are rarely actually optimal. So our optimal design may tell us that we need a sample at 4.37 hours. And we're not going to take a sample at exactly that point. We're going to construct some interval around that. So we do that whether or not we're using optimal design. We can, if we're writing a protocol that specifies a time at 1 hour, we might specify a window of, say, 15 minutes either side. So this is to add to practicality in the clinic when we take our samples. So we can do this with optimal design. Yeah, we can't always collect our samples at precise times. We can optimize these windows depending on the tool we're using, or we can determine them manually. So you can manually say, okay, I think we would use a 1 hour window here or a 15-minute window here, and then look at the impact of that window on the result, meaning the impact on the standard errors that you can expect. So there's a number of tools that we have available This is a table from an increasingly out-of-date paper from 2014, which showed kind of the landscape of the optimal design tools at the time. I'm talking today about PFIM and PopED. I'm not sure if the others are still being actively developed. I didn't find anything in a search. One thing to notice is that if you look at the language, PFIM was in R, everything else was in MATLAB. So certainly the landscape of the languages in pharmacometrics has changed since then. So the two ones that I'm looking at are PFIM, which is still in R, it's now an R package, PopED, which is also now an R package. There was one notable exception from that paper, one tool which has been introduced much more recently, which is the non-mem dollar design block. I'm not going to talk about this today because for one reason, Bob Bauer gave a nice webinar on this a couple of years ago as part of the Mathematics and Computational Science Interest Group webinar series. And there's a link here to where you can watch that webinar. There's also a great paper, a tutorial paper by Bob Bauer, Andy Hooker, and Franz Montre, who are the authors of the PopED and PFIM packages, which go through a number of examples using non-mem design. So this is a great option if you're a non-mem user. If you have your model in non-mem, it means you don't need to translate that model to another language. But yeah, I'm not talking about this today for a couple of reasons. One, because there's already a webinar on it, and also because I wanted to focus today on free and open source tools. So the first tool I'm looking at is PopED. There's a link to the website here with some fantastic documentation that goes into a lot more detail than I will share today. It was originally in something called O Matrix and MATLAB. Now it's an R package. And then there's PFIM. Again, I have a link to the web page here. This was previously a collection of R functions, but has recently been collected together in an R package for version 5. There is also available a GUI called PFIM interface, which is a previous version, so it's not as up to date as the R package. Okay, just a brief comment on simulations. So I mentioned before that we always want to confirm these results with simulation. So what I mean by that is SSE, stochastic simulation and estimation. So we take our model and our proposed design, we simulate many replicates of that design under our study, and then we refit our model to that for each replicate and then summarize the results. So we say we get 500 estimates of clearance from one for each of those replicates, and we look at how much precision and bias we get depending on that design. So I'm doing this for our examples that I'll walk through. So I'm using a BBR, which is a Metrum package for model management, and summarization and things. And then I'll use mrgsolve to do the simulations here too. So let's start with a simple closed form PK model. So there's no ODEs to solve here. So we have a drug that has been studied in adults. This is a fictitious drug, and now we're designing a study in pediatric patients. So the objective is to evaluate the PK in the new pediatric population, but because they're kids, PK sampling is going to be sparse. So we want to make sure that the samples are timed so that we can sufficiently estimate the PK parameters in these kids. So we're going to take 12 subjects, age 6 to 12, with a body weight of about 32 kilograms, treat them with 10 milligrams daily of this drug for 24 weeks. And we're going to propose this sampling scheme. One sample on day 1 at around Tmax, which is about 5 hours for this drug. And then we'll take pre-dose samples on 3 occasions, and then a final sample 1 week after the final dose. So the model is a simple 1-compartment model with first-order absorption. I'm including fixed weight covariates here on clearance and volume, variability on all of our PK parameters, and this combined additive and proportional residual error. So for a typical subject, the PK profile looks something like this. We have quite a short half-life, so we reach steady state very quickly. We have a Tmax around 5-6 hours. All right, so let's check your intuition on this. So without looking at optimizing this design, which do you think of the following designs is going to give you the best standard error for Ka, the absorption rate constant? We're going to go back to adults. We're going to assume only a single dose here, so there's no multiple dosing here, just a single dose in a 70 kilo adult. So I'm going to fix the last 3 points of this design, so 24, 48, and 96 hours, and only worry about where this first sample is going. So the first option here is to put that sample at 1 hour. So you can see where that occurs in the absorption phase here. Option 2 is at 4 hours, approaching your Cmax, and then at 6 hours, right around your Cmax, and then 1 at 12 hours after the Cmax. So see if you can think, which of these do you think is going to give you the best estimate of Ka, the absorption rate constant? And if you picked design 1 with the first sample at 1 hour, you are correct. This has the lowest standard error according to PopED. Once we generate that information matrix, calculate the standard errors. This one is clearly the best one. And I think our intuition for most of us, this would serve us well. Obviously, if you want to estimate a parameter describing the absorption, we want to take samples in the absorption period. But our intuition doesn't always work. And I'll show you some examples of that. That's why we use optimal design. Okay, so the PopED setup, it requires you to specify a number of functions in your R script. You need to specify the model in terms of the model structure, the parameter model, including variability for between subjects and between occasions, if there's any, and a residual error model. And there's a function that collects the model functions together with parameter values and everything related to study design, say doses and number of subjects and so on. And it creates what's called a PopED database. So once we have this object created, so that's what I've called here, the PopED DB. So this database contains all of that information now. You can use, let's start with just plotting the response for our initial design. So there's this function plot model prediction. So we feed in that database, give it some arguments, and then generate this nice plot. So this is showing us the initial design in the points here and the profile given by the line. So this particular model is actually split up into 2 different models. Remember, this is a multiple dose study. We have studies samples on day 1 and then at pre-dose and then after the final dose. And we reach steady state very quickly. So we're going to define the model in terms of the day 1 PK, which is just a single dose PK model, and then the steady state PK, which assumes steady state, obviously. So that's why this plot is split up this way. So we have our sample at 5 hours on day 1. This point here is 24 hours. So this is 24 hours after each steady state dose. So these are the pre-dose trough samples. And then 1 sample at 1 week past the last dose. Okay, so how does this design perform? So first, we generate the official information matrix with this function here. We can look at that matrix itself, or we can just look at the determinant. So here's the determinant. This doesn't actually tell us anything useful until we start comparing this to other designs. Or if we start optimizing the designs, this is what we're trying to maximize. But the useful information we can get out of this at this stage are the relative standard errors using this get RSE function. So immediately we see for each of these parameters, for most of them at least, these standard errors are incredibly high. So looking at clearance here, this is about a 300,000% standard error for clearance, which is clearly not acceptable. So let's see if we can tweak one of these time points and look at the impact on the standard errors. So I'm doing that here by just updating this object by feeding it a new set of sampling times here. So I'm not touching the initial time, leaving that at 5. So the pre-dose samples, they're 24 hours after the steady state doses. I'm going to just shift one of these back from 24 to 23. I'm going to leave all the other time points the same. And we see immediately our clearance standard error has come down incredibly. And this is where my intuition at least starts to fall apart. Why would moving this time point 1 hour have such a big impact on our clearance and even the other parameter estimates? So one of the reasons is that in optimal design, we talk about things called support points. It's the unique time points. So before we only had 3 support points, 5 hours. These were all 24 hours. So that means a single support point and then 168. But if we shift that, we're adding another support point, which improves our design. But we're still not on the way. Some of these standard errors are still very large. We look at V and Ka. So let's try to optimize that design. So we start from our initial design. This is what we had before, and we specify some windows. I don't want to use the word interval windows, some intervals around that, which the search algorithm can search over. So for example, for our sample on day 1, our initial point was 5 hours, but we can specify an interval of 0 to 6 to say that, give me the design which maximizes that determinant. Your first time point can be anywhere immediately after that first dose up to 6 hours after the first dose. And similarly, we put intervals around the other time points. So we can have up to 1 hour before pre-dose and anywhere from 4 to 7 days after the final dose. And then we run this through PopED Optim. And this is going to run through a barrage of optimization algorithms and give you the output. So there's a fair bit here, but I just want to focus on a couple of things. First is the optimized sampling schedule. So recall that we have 2 separate models here. Model 1 is the day 1 PK, model 2 is the steady state samples. So the day 1 sample is at around 0.3 hours, so around 20 minutes past the first dose. So this has pushed that sample all the way down to just after that initial dose. So this is one of the attributes of optimal design, is that especially de-optimal design, it tends to push your samples towards the boundaries of the intervals that you give it. So we specified from 0 to 6 from that. It's gone down almost all the way to 0. Our trough samples mostly unchanged. And then that final sample after the final dose has gone from 7 days all the way down to the lower end of that boundary at 4 days. And let's look at the impact on the standard errors. So this column here gives you the initial standard errors for that initial design. So these are the numbers we've seen before, very large. And these are the optimized standard errors for that optimal design. So given these constraints, we can improve the standard errors, but our design is certainly not good enough yet. Okay, let's look in particular at this Ka standard error. It's still very large. So we would think if we add, just like in the little quiz I gave before, if we add another sample in that absorption phase, that would improve our design. So let's try that. Okay, so I'm going to leave most of this as before, but I'm going to add one more sample here after the final dose, starting at 72 hours, but I'm going to let that vary anywhere from 0 to 168. So anywhere from immediately after the final dose to 1 week after the final dose. And then I'm going to include one sample fixed at 1 week after. So this is the lower and upper limits are the same. So this is not going to move at all during that search. So remember, given that high standard error on absorption, we're hoping for a sample earlier on, which will improve that Ka estimate. Here's our initial design. I'll skip over that. Let's look at the optimized result. So again, that day 1 sample is pushed down to close to soon after that dose, around half an hour this time. We have our trough samples. And then there's that fixed final dose sample. And then we have this. So the extra sample, we allowed it to vary anywhere from 0 to 168. Has not gone down to close to 0 again to give us a better Ka estimate. This is now 41 hours after that final dose. But we can see this is still actually giving us a really good estimate of Ka. So again, my intuition fails here. I don't know about you, but with only one sample still in that absorption phase, we're able to get better estimates of absorption. So these models are complicated. The surface of this this design criterion is very complicated. So when we start to try to use our intuition to pick these sampling times, oftentimes it does fail. All right, so some of these standard errors are still on the high side. So these D underscore parameters are our between subject variabilities. So that's why we have separate CL and then DCL. So this is our variability of clearance, which is on the high side, especially Ka and V are pretty high. So we would probably want to go back and revisit our optimization schedule here. I will point out though that this is a very fast procedure, especially for this simple model. This took us 20 seconds to evaluate thousands upon thousands of designs and pick the best one. All right, so we're not going to take a sample at 41 hours. So if we assume that our doses are given at 8 a.m., 41 hours after that last dose means you're taking a sample around 1 a.m. And I don't know about you, but I'm not taking my kid for a blood sample at 1 a.m. So let's move this back. Let's see what happens if we create what I'm calling here a practical or near optimal design by just shifting these time points around a little bit to make this a little more palatable. So I'm going to move that time point in particular to 32 hours after the last dose. So all the way from 41 to 32, this is now sometime in the afternoon. And without optimizing, I just want to check this one design. And this is fine. I mean, it's still not great in terms of these parameters. These have been bumped up a little more. All of the other standard errors, they're a little higher, but they're still well within the range of acceptable. But again, for a practical design, we're not going to take a sample at exactly 0.5 hours or exactly 32 hours after a dose. So let's generate some intervals around those. And there's a function available in PopED called plot efficiency of windows, where we take our design, we construct upper bounds and lower bounds on each of these time points. So for that first sample on day 1, I'm going to assume a window of any time between 15 minutes before and 15 minutes after we can take a sample, and so on for the other time points. And then PopED will then take uniformly, randomly sample within each of those intervals a new design and calculate the standard error again for that parameter. So for example, for clearance, we do this 100 times. So instead of taking a sample at, so our final design here was 0.5, instead of taking a sample at half an hour every time, we take 100 samples anywhere from half an hour, so from 15 minutes to 45 minutes, and so on for the other time points. And we can see the impact on the clearance standard error. So that's the y-axis here. On average, this is around 10%. It's not deviating by much more than about 0.25%. And you can see for the other parameters, relative to the relative standard error, there's very little impact by deviating from our almost optimal design, which is good news. Okay, so we always want to check this with simulation. And this is because of what I mentioned before. The optimality criterion that we're using is an approximate lower bound. So the number we're getting from PopED or PFIM, which is the numbers on the left here, in the first column here for each parameter, are not going to be what we see when we actually simulate under these designs. So we do one set of confirmatory simulations at the end, and that's the RSEs in the second column. And we see, indeed, for I think every case here, the numbers that we're getting from our simulations are similar, but they're a little bit higher. So this was about 20% for, I think this is our volume parameter. This has gone up to about 30%. So this is something that you do want to check every time. If we're getting to something like this parameter here, so a variability parameter, we can be a little bit more relaxed about our standard errors for these because they're not always the easiest to estimate. Once we start to get to this kind of range, we we want to be really cautious of this in the simulations. You can see this is actually getting much higher, and this parameter here is clearly was not great to begin with, and from simulation we're even above 100%. So yeah, given this result, I mean, I probably would have updated this design just given what I got from PopED. But once you check that in simulation, if in the rare case that you do find that this has a huge mismatch, then you'd want to go back to your optimal design tool and revisit the constraints. Okay, so let's go through the same model, but with PFIM. The approach overall is quite similar. The code is going to differ, obviously, but we start by defining our model. And again, there's three parts to the model. There's your model structure. That's the model equations object. There's a model parameter, object, which defines your variability terms for the parameters. And then there's the response object, which includes your residual error model. So you combine all of those together into a statistical model, and then you combine that with your design information, which would be your sampling times and dose administration, and you collect them together in what's called a PFIM project object. So similar to PopED, where we had the PopED database, now we're working with a PFIM project. I will say again, there are examples of this on the website with the PFIM documentation that will walk you through some nice examples too. Okay, so just like we did with PFIM, we can take that object, so I'm calling that here my project that I've just put together, well, actually Romain and Julie put together, and we can give us an initial plot of these, the initial design that we specified. So this was our day 1 sample, remember, at 5 hours. Then we have our 3 trough samples, and then we have our final dose, sorry, our final sample, which is 1 week after that last dose. So this model has been put together a little differently. Instead of having a separate model for day 1 and steady state, we're just using straight multiple doses. So we're assuming we're at steady state by close to a week after our first dose, which is fair for this model. All right, we can evaluate our information matrix. And there's a lot of data that we can get from that evaluation. It gives you all of the information about the design, the information matrix for the fixed effects, random effect parameters, correlation matrix, and then it will tell you the determinant again, which remember is not useful on its own. But what we do want to look at to begin with are these standard errors, particularly the relative standard errors. And again, we see very large relative standard errors for this initial design. So remember, this is, with some subtle differences, this is the same model and design that we used in PopED. So we're not expecting, given what we saw in PopED, we're not expecting good standard errors for this design. We can also show this graphically, these standard errors. There's this plot RSE function, which shows you a bar chart of the standard errors. And this has it split up because of the huge differences in scale of these standard errors. You can see for Ka, we're up here in the 800,000s. All right, so let's optimize this design. Just as we did in PopED, we set up an initial design and then construct intervals around those times that we will search over, and then run the optimization, which in this case is using a simplex algorithm. So that the options for search algorithms will differ slightly between these two packages. But again, you can always change the options in each package to use a different search algorithm. And here's our result. Again, let's just look at the standard errors quickly. These are better than what we saw before, but they're still rather high, especially for these variability parameters. So let's tweak our design again by adding another post-dose sample after the final dose. Remember, we fixed that last sampling time at 1 week, but this one varied. This is now anywhere. So the last dose now is assumed at 1 week, 168 hours. So we give it an interval from 1 week to 2 weeks. So it will allow us to sample out with that final sample. And now again, we see a much improved set of standard errors, still a little on the high side for these variability terms. All right, so again, once you have these results from PFIM, you would go through the same simulation procedure to check those results. So let's move to a next example, which is an ODE model. So I have another fictitious drug that I'm studying in humans for the first time. So I want to study a wide dose range, 0.03 to 10 milligrams. I'm going to have a small number of subjects in each dose group. And here's our proposed sampling scheme. The model is now a little more complicated. It's a 2-compartment model with nonlinear clearance, which means that we no longer have a closed form solution. We need to use differential equations. So for this, I'm going to use mrgsolve to set up those ODEs. There's a number of options for doing this in PopED. There's a number of packages for solving ODEs, but something like mrgsolve and rxode are great choices which allow you to compile the model and it runs a lot faster. So here's this model set up in mrgsolve. Here are our differential equations for the central compartment, which shows you the nonlinear clearance and the linear clearance, and then our peripheral compartment. And then we capture CP, this concentration in the central compartment. So once we have this set up in mrgsolve, we can create a function that PopED can use. So that's this function here, which sets up dosing and observations. And then ultimately, this line here is doing all the work. This is the mrgsolve simulation function. So it takes our design information and then our parameter values and then spits out concentrations. We do some reshaping of that. So we take that CP plasma concentration object, reshape it into a form that PopED can use, and then it's just another model as PopED knows it. So again, we plot the initial design so you can see this nice, pretty spread of doses from low to high, and the points again are the initial design points that we chose. So how does this fare in terms of standard errors? It actually looks pretty good. So we've taken this is a first in human study. We're allowed to take pretty frequent samples, and it turns out that this is actually a pretty good, we get good estimates for most of our parameters here. Some of the variability terms are again, maybe a little on the high side. So we want to check with simulation. Before we do the simulations, again, we can construct the sampling windows around just to make sure that any variability within these windows is not going to affect our standard errors, and they don't, again, in this case. And let's check our results with simulation. So these are the standard errors from PopED we just looked at. And the second column here is showing you these standard errors that we get from simulation. And again, for most parameters, we see little to no difference. However, if we look at theta 3 here, which corresponds to the Km parameter in the nonlinear clearance, there's a pretty big discrepancy. So we were expecting a really good estimate, really precise estimate with an RSE of around 8%. When we actually run this in a simulation, we're getting close to 40% standard error. So for a fixed effect, for a theta parameter, this is maybe a little too high. So we would want to go back and revisit the design. So this is, I think, a good example of why you really want to confirm these with simulations before actually implementing the design. So we do a similar setup in PFIM, although to define the differential equations, we need to do this in R with what are called expressions. So, we have the same differential equations set up, but they're defined using these expressions. We collect them together in our statistical model, like so. Again, there's the inbuilt function to plot that initial design, and this is helpful for troubleshooting to make sure that your model and design is set up correctly, so you can have a visual indication of what these results are. And then we evaluate this design again. We see, again, very good standard errors, but again, we will want to check that with simulation. And here again are our standard errors shown graphically. So you see this time we don't have to break up that y-axis into multiple segments because these are all reasonable standard errors this time. So one more example, I want to do another ODE example, but for a PKPD model with a lot more parameters, a lot more differential equations. For this, I'm going to use a real drug, filgrastim, and design a study with 3 dose levels, dosing daily, 10 subjects per group, with dense sampling for both the PK and the PD. So for the PK and neutrophil counts in this example. So the model is taken from this publication, which has been published on DD Moore, and then Kyle Barron has translated this to mrgsolve. There are links if you'd like to take a look at the actual model code, but it's a lot more complicated than the last one. So I won't be going through it, but I think it has something like 14 differential equations. Here's the structure of the model. So we have our PK concentrations acting on the neutrophils. So these are our neutrophil precursors. And then we have the drug acting via these stimulatory indirect response models. So we have SC50 parameters and 2 Smax parameters. So that these parameters here are really what I guess define the effect of the drug on neutrophil count. So for example, this is what the model looks like for a big range of doses. We have the PK response on a log scale here, the neutrophil response on a log scale here. And we have a wide range of doses. Remember, we want to test these 3 doses, 1, 3, and 10. So we've set up this design and model in this PopED database, and we can evaluate that these standard errors. And again, we have a lot more parameters, so I'm not going to go through all of them, but these are all looking pretty good. If we focus on SC1, is that actually the SC50 parameter? It has a pretty reasonable standard error, around 20%. Again, we do need to check this with simulation to make sure that that approximation and the lower bound is not steering us into a bad direction. And our Smax parameters are actually pretty low, 6 and 7%. So another quiz for you, another time, a chance to check your intuition. So given the results that we've seen, remember we were looking at 1, 3, and 10 doses. Do you think there are any better doses for estimating those SC50 and Smax parameters? So is this our best design? Maybe we want to push all our doses down by a half log. So let's look at, say, 0.3, 1, and 3. Maybe we want to push all of our doses up, 3, 10, and 30. So do you think lower doses or higher doses on average are going to give you better estimates of SC50 or Cmax? So the answer is, it doesn't make a whole lot of difference in this case. We already had good standard errors to begin with. The Smaxes, I think this is the easiest one to check your intuition on. You're going to get better Smax. This is like an Emax and an Emax model. You get better estimates of those if you push your doses higher. And we do see that our standard errors come down slightly there. We're going to get worse parameters if we push our doses down. But again, these are all in a good, reasonable range. Now, SC50 actually doesn't move much at all in this case. So either of these designs would be adequate. Okay, let me wrap up. So hopefully what you learned today is that optimal design can be a useful tool. It's not perfect. We do need to check this with simulation, but it is a very useful tool for exploring and sometimes optimizing, not every time, study design options. But I've said this many times, I do want to stress this, always, always, always run confirmatory simulations. Don't trust the results of these tools blindly without running a simulation because of that approximate lower bound on that information matrix. And it's not just for PK sampling. So a lot of people think of optimal design as equivalent to optimizing PK sampling. But as we saw with that last example, we had dense sampling. So I wanted to take the PK and the neutrophil count sampling times out of the equation there so we could focus on what mattered in that case, which is picking the doses. So we can optimize doses, we can optimize the number of subjects, we can optimize the dosing regimen, whatever's defining the design of that study, you can optimize it with these tools. There's a lot that we missed. Dealing with parameter uncertainty is very important to do a kind of sensitivity analysis on, I don't want to call it sensitivity analysis, but when you're very uncertain in your parameter values, I would recommend you try one of the other optimality criteria. You can also deal with the uncertainty in the model structure. If you don't know if it's a 1 or 2 compartment model, for example, there are optimality criteria to help you distinguish those. You can ignore unimportant parameters, and there's basically an alphabet of other criteria. I also didn't talk about pretty much every option available in both of these packages, and I gave you a high-level introduction here, but I'll make these slides available. There are links in here to the web pages, so you can check out that documentation. So here's some links and some references. And with that, I'd like to thank you for your attention, and I'd be happy to take any questions.
Thank you, Dr. Waterhouse. I'm going to stop the recording and then pass this over to Julie to navigate the Q&A. So thank you again for what's a really nice talk.
All right, thanks.
Yes, indeed. Thank